Okay, so welcome everybody. You've successfully negotiated your entomology part of the course, bar obviously your insect collections, and I'm sure you all want to do, those who have to do their fact sheet, those who are doing the higher course code, I'm sure you all want to do it in entomology, or not. Anyway, so we are about to start the second part of this unit, which is going to focus on plant diseases. So in our lower life forms, we're going to deal with some of them that are somewhat lower in their life form than our insects. A lot of the focus, in case you can't remember, I'm Callum Wilson, so I think I turned up in the first week and introduced myself. So we'll be covering this component of the course. My main office is actually based out at Newtown rather than here in Sandy Bay, so if you do want to catch up and discuss anything, it's usually best to send an email first, and then or before or after the lectures, which is a good time, or the prac classes, which is a good time to catch me. Because I may not necessarily be on campus if you just roll up to an office and try and find me, but if you do need to ask about anything, you're more than happy to meet with you and talk about it. The major focus of what we're going to cover in the plant disease section, we're going to go over some of the major entities biological entities that induce disease, and that we tend to study. But we're going to have a major focus on diagnostics, on trying to understand the cause of disease. And indeed, your prac classes are primarily going to be based around that focus as well. So we'll discuss that in the prac classes itself, but we'll introduce what diseases are, but a big portion of your prac class will actually be doing what we call a disease clinic, where you'll have some samples, and it's your job essentially over 3 or so weeks to try and work out what it is that caused that particular disease. So we're going to get to that stage. But let's start with some basics of what is a disease. Might sound like a silly question. It might sound like something, disease is just a sick plant. It is, but what I want you to do is break that down. What we're going to do is we're going to spend a couple of minutes, so go and talk to your neighbours, 2s or 3s, whatever, and think about these 3 questions. So spend a couple of minutes having a chat with each other, and I want you to think of what is it that causes disease. What are the types of entities? What are the things that actually make plants sick? Number 2, what kind of damage is a plant disease? How do we define the damage? What kinds of damage would we call disease versus perhaps something else? And the last thing, if your definition of what is a plant disease is something that's not healthy, what is a healthy plant? Which may sound simple, but actually is a little bit trickier when you come to define it. So in the textbooks, there's a really big convoluted description of what plant diseases are to try and define some of those things. And then there's no necessarily correct answer. All the different textbooks actually describe it slightly differently. But okay, we've got a couple of minutes. Go and have a chat to your neighbours, and we're going to try and answer some of those questions. And don't cheat and look at the rest of your notes. That's just cheating. That's why I made them so small so you can't read them. Okay, so we might start again. You can keep thinking about it, and we'll toss up answers as we go, and see if we can get a bit of a list happening. So, what sorts of things cause disease in plants? Who's going to start me off? Someone at the back.
Bacteria.
Bacteria. Let's have some bacteria. Next. Viruses. Viroids. Sorry?
How do you pronounce it, sir?
Viroids.
Alright.
Yep. Sorry, was there another one after that? I didn't hear. Virons?
I don't think so.
No. But there are virusoids, which are kind of weird, but we won't worry about those. Fungi. Come on, keep going.
Some of the algae.
Algae? Nematodes. Anything else? We don't have to be comprehensive. But
Humans.
humans.
Environment factors.
Environmental factors.
Animals.
Animals. Getting a fairly broad list there already. That's good. And as I said, there's no right or wrong answers. In our plant pathology textbooks, as a plant pathologist, we tend to deal with living things only. So all those nutrient deficiencies, all those lightning strikes, all those too hot, too cold, frost, we tend to think of as disorders rather than diseases. Does that mean they don't damage plants? They don't cause... no. So more holistically, if we're talking about plant performance rather than plant disease, these are incredible. In fact, when we do talk about plant disease, the environmental factors are absolutely crucial, even when you're talking some of these biological entities, and we're going to discuss that in a minute. Within plant pathology, the discipline, we kind of leave those out as the primary cause of the problem. But that is a definition for plant pathologists, and probably narrower than you'd want to as a plant husband. If you're responsible for growing a healthy crop, you'd want to think much beyond just some of these other entities. So we tend to exclude the abiotic or the environmental things, but even that has problematic. And here's my example here. There was one. It's actually shortly after I arrived in Tasmania, many years ago. Was actually in a plant disease clinic, and that year there was all these samples coming in, and they all had fungal rots. They all had lots of Fusarium rots and Rhizoctonia rot, all these fungal rots in the roots. all with generally mild pathogens, but you isolate all these fungal rots. It was a really wet season. The fields were waterlogged. You could argue that the primary cause of all of those diseases was the fact that we had lack of oxygen, waterlogged soils that allowed all these opportunistic fungi to come in and cause disease. So you could perhaps argue that it wasn't the fungus that was actually causing the disease. They were the ones that actually invaded and generated the damage, but it was the environmental condition that actually was the primary cause. So again, that's the definition from a textbook. I want you to think a little bit more globally in your thinking in terms of what is the actual factors that cause disease. As I said, disorder is usually what people use to describe those that are just caused by nutrient stresses or by frost damage or other things, spray damage, etc. Similarly, you've just done entomology. They're a biotic agent, but they're covered by entomologists. So plant pathologists say, no, you can keep those. We'll just call that plant damage when the insect eats it. But when a fungus eats it, no, that's a disease. Again, it's splitting hairs, but in reality, the insects are causing similar damage, and then it gets complex when you've got insects that actually feed on the plant, but also transmit pathogens like viruses and cause disease. So we are talking about a complex system. Similarly, humans and animals, they certainly cause damage. People, you mow your lawn, that's pretty severe damage to the grass. That's generally not considered a disease by our definition, but obviously it is affecting how healthy the plant is and its performance. And similarly, when animals predate or feed on plants, they cause damage. So traditionally, at least with in plant pathology, all these guys here, and nematodes would be considered some of our major causal agents that we study. We'd exclude what people do, we'd exclude what animals do, the environment, and algal probably not directly. There are some things that actually can release toxins, and those toxins can affect plant performance, but not as an infective agent. But we are talking about an incredibly diverse array, even in these biotic things, an incredibly diverse array of orders. Entomology, you deal with insects. Gee, they're just animals. Here we've got animals, we've got nematodes, we've got little worms. We've got fungi, completely different order. We've got bacteria, completely different order. We've got viruses that aren't even living things, officially. They're not cellular. Incredibly diverse agents. We've even got plants. Plant pathologists actually also deal with parasitic plants, which are kind of weird, not that common, but can be entities. Okay, what was our next question? What sort of damage? So again, we've got the what sort of damage should we consider if we're talking about not being a healthy plant, and then we've got the what sort of the damage do the plant pathologists actually consider is related to plant disease. Sorry?
Yellow buff leaves.
Yellow.
Necrosis.
Sorry, this is making lots of noise.
Stunting.
Stunting.
Curling of leaves.
Should switch that off, it's making noise.
Rotting of roots.
Rotting, all that sorts of stuff. Let's go on to the next slide. Generally, things that actually damage and reduce the performance of the plants. There are some things, however, that again sit on that greyness of definition. you could argue that something that relates, if we're dealing with all these things, if they infect a plant, surely that's a disease. Once you've got an infection of a plant with a virus, it must be causing disease on that plant, and so after the infection phase. But there are some interesting examples. You can get infections that don't actually cause negative impacts on the plant. So rhizobia, these are bacteria. They infect roots in pretty much the same way as a pathogenic bacteria would. They invade the root. It just so happens that when they invade it, they start fixing nitrogen and actually provide nutrition to the plant, and the plant grows better. Is that a disease? It's an infection event by a biotic agent. We wouldn't describe that as a disease because it isn't detrimental to the plant. So it hasn't caused detrimental damage. It has changed things. You certainly know those nodules are not natural. It's certainly physiologically and physically changed the plant, but not in a negative manner. Similarly with mycorrhizal fungi. So these are fungi that actually invade the roots. They can actually physically infect the roots, but by doing so, and they derive nutrition from the plant, so they are parasitic on the plant, but they also, their network allows sequestering of things like potassium from the environment and actually feeding the plant. So both rhizobia and these mycorrhizal infect plants. They derive nutrition from the plants, much like all these other pathogens that cause disease, but they also provide a beneficial effect, and so the net is a positive. So we describe these as not pathogens because they're not causing suffering. Pathos is Greek for suffering, so a pathogen should be causing suffering. Similarly, there are some infections that you have your so-called pathogen invades the plant and you see no obvious effect. There are quite a number of viruses that give what we call cryptic or latent viruses. So they invade the plant and you don't see any leaf spots, you don't see any yellowing, you don't see necrosis, you don't see any stunting. Is that diseased? If it really is not negatively affecting the performance of the plant, you'd probably argue maybe it isn't. You've got to be careful though, because sometimes those plants that look healthy, if you really compare them to an uninfected plant, they might actually be really, really mildly stunted. They might have lost 10% of their performance. You just can't tell because they don't have rotten leaves. You don't have leaf spots. They're actually hard to tell. So we do have a number of pathogens that nibble away at the edge of plants, and we tend to think of them as not pathogens at all, but they may actually be causing significant yield loss. A pathogen, or we know it's a pathogen, but one, probably the most important pathogen in the potato industry at the moment is a disease called powdery scab that makes the tubers look ugly. But that was all they thought it was, until they realised that the root infection phase of that disease, which they thought, who cares, it doesn't do anything, is probably nailing them by about somewhere between 10 and 15% yield. All of a sudden that adds up to a hell of a lot of money that they're losing for something that wasn't causing major rotting. And they didn't really notice it stunting plants, but when you actually do those comparisons, it was. Anyway, what else? Well, this is an interesting one. What happens if you actually get an infection, you get yellowing or stunting or some of these symptoms, but they're actually beneficial for the use of that plant. So, tulip breaking in tulips. Here's our Rembrandt painting. And these are all virus infected. And they look kind of pretty. Back in those days, these guys here were worth a fortune. People would pay a lot of money for a single bulb that produces a stripy flower because they thought it was so beautiful. Nowadays you can't sell them because of course they know it's diseased. Back then they'll do things, really, really lucky girls might get a bulb as part of their dowry when they were getting married because it was worth a fortune. Anyway. It back then was regarded as a beneficial thing. So even though it caused stunting, reduced yield, it was actually regarded as beneficial. There are other examples. There are some shrubs that actually have this lovely variegated foliage, and people buy them and plant them in the garden because they look pretty. It's because they've got a virus in them. They're actually stunted, they're actually diseased, they're actually not performing optimally. But if you took the virus out, they'd just be any old plant and no one would want to buy it anymore. So occasionally you can have diseases that are beneficial. The other aspect in relation to what damage, and this kind of reflects when we're removing out environmental factors from the plant pathologist definition, is something about the permanence of the damage. Is it an ongoing irritation, or is it something that occurs once and it can grow out of? A frost event that causes damage, but then it can regrow. In some textbooks, they regard that as not a disease because it's a one-off thing. But even that definition is grey, because even with some of these guys, you might get an infection, you start to get development of a disease, and then the environment changes and becomes less conducive for the disease. The pathogen stops, the disease stops, the plant grows away from it and becomes healthy again. Is that not a disease? I hope what you're getting from this is that the answer to that what is a disease question is not as clear-cut as we might first think. And I want you guys to be very open in your thinking about what plant disease is. You read plant pathology textbooks, they'll be quite narrow in their definition, and this course will be focusing on that definition. But as plant husbanders, or what's the term? As plant managers, if you're managing plant growth, you need to be thinking much more holistic. It's a waste of time focusing on the fungi without considering the environment as well. Up. What's a healthy plant?
Healthy plant which do its physiological process normally.
Right, yep. So it grows to its optimal performance. So you've got a plant, it's got a genetic potential to grow in a manner. Does that mean, how many plants in the environment do you think grow optimally? Aren't suffering at all from anything? Probably none. Everything is limiting. You know, there's nutrient limitations, there's light limitations, there's competition, there's temperature limitations. You could argue, are all plants diseased? Well, that's a pretty crappy definition. If every plant's diseased, it keeps plant pathologists in business, that's good. But it's not a very practical definition. If you're growing a crop and you've got a wonderful crop and you go, no, they're all diseased anyway because they might have grown an extra 0.5% yield if we gave them, you know, if we got an extra degree in the day temperature or something. So what we need is a much more practical definition of health. And now we get to some of those definitions that are in the textbook. So one of the books I think we recommended for the course, it's getting old now, but it's by this American guy called Agrios, George Agrios. Now this is a fairly wordy definition, but he describes a disease as, I need a better stick. There we go. Any disturbance brought around by a pathogen or environmental factor. So this guy's good. He's actually bringing these guys into it. Other textbooks leave them out. So Agrios is a bit more holistic. That's good. So anything caused by a pathogen or environmental factor that interferes with, essentially stops the plant growing to its full potential. So it has to interfere with the way it makes or translocates or uses food, nutrients, and water, such as that it changes appearance or yields. So it's saying if it's not causing any symptoms, it's not a disease in this instance. So yields or appears different or yields less than a normal healthy plant. Now that's a bit of a cop-out, but he does follow up and say a normal healthy plant is one that is able to carry out its physiological functions to the best of its genetic potential. On that definition, every single plant's diseased. But I think we can adapt that somewhat and maybe say instead in practice, any disturbance that leads to unsatisfactory plant performance. And you can define that depending on your purpose. So if you're a grower, if you're a farmer, it might be, I need a plant to perform at a certain level to get an appropriate yield, and a few nibbles around the edges that don't really affect my yield terribly much is not going to be considered a plant disease. It's more if you're actually getting something that's going to give us an unsatisfactory outcome. But anyway, so the purpose of this first session really is to try and make you think broadly. Don't limit your thinking. The plant health management concepts go way beyond discipline borders. Plant health, we're talking entomology, we're talking plant pathology, we're talking plant agronomy, and all of these relate to how plants perform. Right. Next exercise. When we're dealing with unsatisfactory plant performance, what makes it unsatisfactory? It's usually because it costs us something. What do we mean by cost? And if you're trying to determine, gee, this is a nasty, horrible disease, it cost this amount to the industry. How do we define what those costs are? And once again, how can we think a bit more holistically? Because we've got economic costs and we've got ecological costs, and we need to think broader than that, because if we just solely focus on loss, we greatly underestimate the impact of these diseases on our livelihood, on our communities, and on our back pocket. So, we're going to fill this table in quickly. Let's throw some under any column. Start giving me some ideas.
Reputation.
Reputation. So which one are you putting that under?
Direct. Sure.
I'd probably put, by direct I mean the actual disease itself takes money out of your pocket, so it's probably down here. So, as a grower, absolutely right. As a grower, you suffered a big nasty disease last year, and all of a sudden no one wants to buy your stuff, even if your crop's good this year. Or you were an unreliable supplier because of disease, and now you've lost markets. That is a huge economic cost that's not related directly to how much the fungus ate your plant. What else?
Yield loss.
Yields, yep. So that's going to be a direct cost. So you're expecting to produce so much, you got a lot less.
Did you say quality of yield too?
Quality, yep, exactly. So if you grow an awful lot of apples, but they're all covered in black spot, you can't sell them. Well, you're not going to get them much money for them anyway.
Like demand, like won't go down.
Yep. So reduced demand. And that could be related to a whole bunch of things, I guess. It could be public perception of, I don't like those because they could be dangerous, or it could be they're covered in spots and I don't particularly want to eat spotty things.
Maybe the cost in trying to fix the disease.
Yep. Costs of control. So, and what are some of those costs? Let's expand that out a bit. So, sprays. What else? Labour. Huge one. Biosecurity. Even things like tractors and equipment and whatever else. The actual physical stuff, I mean, that's quite expensive. Biosecurity, the cost of actually meeting the requirements of biosecurity. Quarantine costs. Even if export, it might be, okay, I want to export this, but because there is a disease in my state, I now have to fumigate everything before I send it away, and that's a cost. So we're seeing you're getting a bunch of these. What about some ecological ones?
Human health.
Health. Yep, and that could be in a number of ways. It could be you've got something with a toxin in it that negatively impacts health. A classic example, historical example, would be ergot, ergot of wheat. So this is a fungus that actually eats the grain of the wheat and replaces essentially the grain with fungal spores. But the ergot fungus produces some really interesting metabolites, one of which being lysergic, something rather acid, LSD, speed. So it produces a hallucinogenic drug. Now, eat too much of that, it's pretty toxic. But it also, a great historical example, this is Peter the Great, Russian warrior, sending a huge army through Europe, conquering everything as he went. And he hits a town called Astrakhan, which I think is in Netherlands somewhere. And was about to keep wandering through and taking over the next town and the next next county. And as all invading armies do, they don't carry all their food with them. They just rape and pillage the local environment. So they went to local town. They took all their grain stores. Now they had a bad ergot year, so all of their grain stores were contaminated with ergot. So all of his soldiers, all his horses, and everything else ate all this ergotized wheat. A whole bunch of them got sick. Peter the Great himself had a trip and had all these hallucinogenic things and thought this is a bad sign. He turned around and went home. So affected their health. Actually affected the extent of his dominion because he stopped his invasion.
Soil contamination.
Sorry?
The environment.
Yep. Both by pathogens and potentially by pesticides if you're tossing things in. Anything else?
Expense if you've got reduced use, cost goes up.
Yep. So your inputs. You need to plant more. You need to use more fertilisers to compensate for yields or something. Yep. What have I got there? No. I've lost my cheat sheet. Anyway, I'll go and... actually, I think it's here. There we go. The one I haven't given you yet because of the cheat. I know you'd look at it. What else have we got? Soil contamination. Well, yeah, pesticides in the environment. Lots of species. Dutch elm disease is a nasty, horrible fungal disease of elms, of certain elm trees, and particularly throughout the US. You won't find, there used to be lots of elms, there's actually not that many anymore because this pathogen arrived, it's spread by a beetle, and it goes through and there's no controls. And so all of those particular genus are getting wiped out by this particular disease. Thankfully there's a is it a European or a Japanese, I should know, I can't remember, a different elm species that's resistant, and so they can actually start replacing those. So through Europe, for instance, they still have elms, but that's because they brought in the resistant genus. In the US, they're losing them all. Australia's elms are all these susceptible ones. We don't have that disease yet. If we do, goodbye elms. There's nothing we can do to stop them, apart from replace them with something else. Loss of beauty. I mean, it was a number of years now ago, we had something called the Pine Lake dieback. So in the highlands of Tasmania, there was this Phytophthora that was taking out a lot of the native species. And you end up with all these dead trees everywhere. It doesn't look terribly nice for bushwalkers going through the landscape when you've got a whole bunch of dead trees. So I had all these signs about cleaning your boots and all this sort of stuff. But that was a disease that was potentially causing an indirect cost too from tourism, but was actually reducing people's enjoyment of the environment. What else have we got? We got things like land values can go down, research. They've got to pay me to do research to control these diseases, that costs. Got biosecurity. Here's a good one. Rotation. Why do we rotate crops? Primarily for control of disease, because you build up pathogens in the soil. If you grow peas after peas after peas after peas, you build up these pea pathogens and they start wiping your crop out and you can't yield anything. So we rotate. But what you're doing is you've probably got a crop that's actually the most valuable one. Maybe in the northwest coast, potatoes are pretty valuable. Peas aren't so good, although they're getting better. But rather than growing potatoes every year, where you're going to make the biggest margin on your land, you've got to rotate, because you grow potatoes 2-3 years in a row, all of a sudden you're not making any margins because of disease. So rotation is something we do without necessarily thinking why, in some ways. But it's about disease. So that's a pretty good list. And again, the whole thoughts around this is we need to be holistic and understanding what the costs are. There are, again, in textbooks, quite often the textbooks say, oh, this disease cost $10 million. And that's almost solely due to this. They measured, okay, we wrote off these crops, we lost 50% of our production, and the production was worth $20 million, so we lost $10 million. They've ignored all of this stuff, which actually might be a greater economic cost, might be a greater social cost. We've got loss of employment as well, things like that. I mean, farms might shut down because of a nasty disease. When I was doing my PhD in Western Australia, they got an outbreak of potato cyst nematode, which is really, really nasty, horrible thing. We don't have here, thankfully, in Tassie. But it occurred on a few properties in Western Australia. Those properties are now houses. The way to deal with it, because it was persistent in the soil, this was in the metropolitan area of Perth, was, sorry, you're not growing anything anymore. Well, you're not growing potatoes at least. And so a lot of those have been essentially turned into subdivisions. That's a fairly social impact on not only the farmer and the farmer's family and their future, but that whole community. So a lot of the comments you see about the cost are based on this sort of stuff, and they talk about 30% of production is lost to disease, but that figure can really mean very little. Some of the biggest costs we have are the diseases we don't see. I'd argue things like potato leaf roll virus in potatoes in Tasmania, we hardly ever see it. There are some growers who think it doesn't exist, or does, but it's very, very, very low levels. Does that mean it causes no loss? Not at all, because this is pretty damn expensive. So we don't have to spray insecticides because we've got the inoculum levels really down. But why we've got inoculum levels really down is because of a seed certification system. And the seed certification system costs money. It's all based around virus control. And so we've imposed this system whereby you can only buy certified seed. It costs a lot more than other types of seed, but it's certified to be free or low of these viruses. And that means you can grow a crop with certainty of not knowing that you're not going to get damage with that crop. But you've paid for it. So the disease is not there, but it's costing you. And we need to think of all of these costs because we tend to forget them, and then we tend to consider things not important. So again, seed certification in potatoes, there was at least at some point a number of growers saying, we don't need this anymore. We don't have virus diseases. Why are we spending all this money on certification? Why are we spending all this money, extra money on buying this fancy seed when I can just buy crappy seed that's much cheaper and still get away with it? Because when you do buy crappy seed, the disease comes back and you start losing yield. They forget that they are spending money to actually avoid losing money, if that makes sense. But in the end, we need to get a good estimate of what all of the costs and the potential costs are before we then go and make decisions about what to do about it. If you've got a crop and it's getting a few leaf spots and you're estimating this pretty minor disease is going through and costing about a 5% yield, and that's going to, in terms of, but apart from that, you can live with it, and the yield impact is going to be something like, $5,000 a hectare or something, and you're going to spend $20,000 on fungicides to actually control it. Probably not, unless it's likely to get worse or spread or do something else. So you'd be considering your cost benefits in terms of how you manage it. For most diseases, there might be 20 or 30 different things you could do to actually minimise it, but you add up all those costs and you find out that's not worth it. You might pick some of the most beneficial ones, but work out your cost and benefit in terms of how that's managed. In some instances, it might be you're thinking more broadly. Our poor West Australian growers who lost their farms because they had potato cyst nematode on them. Obviously, the cost to them was much greater than the potential cost that disease would have been if they kept growing potatoes. But that decision was made to protect the rest of the state, the rest of the growers in that industry. And so the benefit globally was worth it. Whoops. The benefit for the individual grower was not actually there. Okay. Where are we at now? Ooh, we're going to run out of time, isn't that good? That's fine. So we'll keep going, and now the next phase I want to discuss is about cause. So we're getting on to the concept of disease diagnosis, and the next couple of lectures are also going to focus on some of the diagnostic tools and some of the principles of diagnosis. Some terms. Etiology. You might come across it. It is sometimes, depending on which, this is the American version, the British version's got an A in front of it. It's the study of cause. So what is it that caused the disease? And it's really all about this. Diagnosis is critical because before you can do anything about it, you've really got to understand what you're dealing with. If you don't understand not only what's the causal agent, but also how it interacts with the plant, you won't be able to devise an appropriate management strategy that's going to deal with it. So it's absolutely critical to know your enemy, to know what it is, and know how it operates, and know its secrets, and know its interactions, so you can then put barriers up to prevent those interactions. And this is a really important concept in plant pathology. It's called the disease triangle, sometimes the disease pyramid. But essentially it's saying, and again, this is focused on biotic agents, of course. You've got your plant, your susceptible host plant. You need one of those. You need a virulent pathogen that's going to infect it, and it's going to interact with the host. And you need a favourable, conducive environment, because and by that, something that's actually going to favour the pathogen and favour the host and favour those interactions. And when all three interact, you get disease. If you get the pathogen interacting with the host, but the environment is not favourable, you may get no disease. It might be, look, it's too hot and dry. Late blight of potatoes, you've got a virulent pathogen, you've got a susceptible host, it's hot and dry, nothing's going to happen because it needs cold and wet. Or you have cold and wet and no pathogen, well, obviously that's not going to be a problem. If you've got Phytophthora, you've got cold and wet, and you've got a resistant host, or you've got a carrot instead of a potato, no disease. So it's that interaction of those three factors that become critical. And we drill it down a bit further. We can look at some of the host factors. So what is it that influences the host's susceptibility to disease? We can have varying levels of resistance, genetic resistance to the pathogen. So it might be that it's got a resistance gene, or it's a bit tougher and a bit more robust. It might even be just the physical nature of it. For instance, there are some leafless, semi-leafless peas And one of the reasons they bred those semi-leafless peas is because when you grow peas in a crop, they tend to be quite close together. You get this highly humid environment when they've got lots of leaves, and that's really good for promoting fungal spread and disease. The semi-leafless peas allow more wind to blow through, a lot more air, a lot lower relative humidity, reduces, because of the genetics, actually reduces the conducive environment and actually decreases disease. So it's that interaction between genetics and environment in that instance that actually stops a disease. Uniformity, that can be genetic uniformity. So a lot of plant disease in agriculture is man-made. If you look in nature, you don't see hectares and hectares of the same species as far as the eye can see with nothing else. You know, you don't have, you've got this huge matrix and diversity and this mosaic of different species, different plant species, even within species, different variants of that species. And each of those are slightly different, have different genetic resistances. If you've got a pathogen that's taking out a eucalypt tree, for instance, it might not be taking out a little shrub next door. So you've actually got potential genetic barriers between its spread, rather than having one big huge monoculture, which is what we tend to have in agricultural systems. So when we plant a field full of soybeans, it infects the first one in the corner, and the rest is genetically uniform. There's nothing to really stop that pathogen moving through the rest of the crop and infecting the whole crop. In agricultural systems, can you influence that? Well, you can, and in some instances they have. So there are some wheat varieties, which aren't varieties at all. They're actually a mixture. So they've actually taken 2 or 3 different genotypes, mixed them all together, and that's their seed line. And when they sow that, they get this mosaic, genetic mosaic in the field, and so that helps to slow things like rust moving through, because rust might be, that particular genotype might be super susceptible, but the plant next door might be a bit more resistant, and so it actually slows the development of disease. So genetic uniformity. Unfortunately, agriculture tends to push towards uniformity. And there are other aspects too. So things like how old the plant is. There are some diseases that are specialists at taking out seedlings. There are some that really hang around and finish the plant off when it gets old. And there are some that can attack it at any stage of its lifestyle. So we're talking about it. The host is a living thing. It's a dynamic organism. It's not just one entity. It starts from seed to senescence. And during that period, it'll vary in its susceptibility or resistance to infection over time. What about the pathogen? Well, the pathogen can vary in its virulence. Virulence is how nasty it is, how easy it can infect, and how quickly it infects, and how much damage it causes. So you have some that are really mild and don't do much at all, and some that are really virulent and cause major damage. So that will be part of how that interaction. How they reproduce. There are some that might produce an aerial spore that blows everywhere, and that can actually spread much quicker and cause greater damage. There are some that, that's the type of inoculum. And there are some that might be things like nematodes. Well, they exist in the soil and they reproduce fairly slowly, and they move from plant to plant within the soil moisture system. They don't actually spread over vast distances. How fast they reproduce is important too. Is it something that can go through multiple cycles in a season and get you an exponential increase in disease, or is it something that actually spreads, it has one cycle in the season and you'll actually get quite slow spread? How does it spread? All of those factors, and there's a range of others, will affect how the capacity of the pathogen to induce disease. And if we look at environment, obviously there's a whole bunch of environmental factors that will influence the conducive nature of disease. So where is it? Is it north facing, south facing? Has it had more sunlight, less sunlight? Is it better draining and drying? Is it sloping? Is it flat? Is it a hollow where water's going to accumulate? Is there too much moisture? Is there not enough moisture in soil, in the air? Is it nutrient deficient? Is it too much nutrients? low or high temperatures. You can even toss in other biotic things. Are there other insects out there that actually are responsible for spreading your particular pathogen or not? So if you're talking about if our pathogen's a virus and it needs an insect to spread it, obviously an important environmental factor is the presence of that insect and what it's doing in the environment. And finally bring it in. As I said, sometimes it's called the disease pyramid rather than disease triangle because there is a fourth factor, and that is time. And it's because we're dealing with biological entities. We're dealing with a plant that's obviously changes over time. We're dealing with a pathogen that changes over time, and even the environment that changes over time. It's not exactly the same conditions every single day or every single hour of every single day. So it's dynamic. Disease is a dynamic process. Just because you've got a conducive environment, a susceptible host, and a virulent pathogen doesn't necessarily mean you're going to get disease if half an hour later things change. So, for instance, there's a lovely disease model for black spot in apples. And what that does is it measures the amount of leaf wetness, and you need leaf wetness for 12 hours before infection will occur. So you might have leaf wetness, you've got the conducive environment, you've got the pathogen already sitting on the leaf, you've got a susceptible host, the apple, but infection will only occur if time is long enough for it to germinate and penetrate. So if in that 12 hours you get wind blowing through and you get a bit more warmth and that surface moisture evaporates, no infection will occur, so no disease. So you need these three factors, but you also need sufficient time to actually allow that interaction to occur. And changing over time can affect, well, having disease at all, but it also can affect the extended damage. It might be if you maintain those conducive conditions and that virulent pathogen for a long period of time, you'll end up with a terrible amount of rot and horrible disease. Or maybe you can change things, or the environment will change, and the disease will slow or stop. And similarly, the type of symptoms you get, you might get greater or less symptoms depending on the length of time that those conducive conditions have been present. Where am I at? We're going to have a break. Okay, 2 more slides, and then we'll have a break. So, as I said, that's kind of what we just summarised. So the host will vary with plant age, the pathogen will vary as it goes through its different cycles, from spores to infective units to resting structures sitting in the soil or whatever, and the environment obviously changes. And this is kind of summarised up with this as another sort of diagram where you've got, no interaction, no disease. It might move in and might move out and get light disease, heavy disease as those interactions change with time. To summarise, there tends to be a strong tendency to overestimate the biological pest. And part of that was in our definitions to start with. We're all talking about viruses, we're not talking about the system. Even when a lot of diagnosticians, they go and say, oh, that disease was caused by Phytophthora infestans. They go, no, it was actually caused by Phytophthora infestans and a wet, cold environment and a susceptible variety for an extended period of time. That's what caused the disease. You need to think of all of those interacting factors, the host genetics, the environmental factors, because it's those interactions that lead to disease, not just the pathogen. You can have the pathogen sitting there, nothing's going to happen if you don't have a susceptible host, conducive conditions for the right period of time. And that's important because when we come to management, it's all about breaking those interactions. How can we separate the pathogen from the host? How can we change conducive conditions? Put in a decent drain to get rid of all that waterlogged soil. All of a sudden, all those minor soil rotting pathogens disappear. They might still be there, but they're not going to cause disease. So if we can break those interactions, then we can control. Last one, I promise, and then we'll have a break. So in essence, if you're a diagnostician, you're a bit of a mixture of a detective, the whodunit, trying, what's the nasty fungus, but you also need to be a bit more of an ecologist and actually understand the environment and the system. If you don't understand the system, you don't understand the disease. So if you're looking for trying to work out the cause of a disease, you need to get clues from a range of things. You need to look at both biotic and abiotic factors. You need to look at the soil type. You need to look at the slope. You need to look at the history. You need to look at drainage. You need to look at more than just what fungus did I find in that lesion. And really, you're talking about taking your skills from soil science, nutrition, ecology, entomology, weed science, etc., to actually make a really good plant pathologist diagnostician. Right, let's have a break. Thank you. So, sorry, I've only given you 5 minutes, but if you can come back in 5, we'll start the next one.